Okay, so I think we're live. So hi everyone again. Welcome to the fourth seminar of this quarantine thermo initiative. I hope everybody is keeping well, keeping safe in this period. So today we got a very interesting talk from Marti. So Marti is currently in exile in Germany in MPQ, but I think he's somehow in the process of moving to Geneva at some point. I wasn't exactly sure what's going on with that, but I think he's somewhere in between the two places, but in Germany formally. As I said, so far great reception on all of the talks. I think today we'll also have another very nice talk. And without further ado, I introduce you to Marty. Marty's going to talk about his recent work on finite time Carnot cycles. Marty, you can share your screen, and I'll be back. All right?
Okay. Good. Is it fine?
It looks okay. Just put it to full screen.
Yes. Okay. So I guess.
Perfect.
Yeah. Perfect. So thanks a lot, John. It's really a pleasure to be here. I mean, thanks for this opportunity and for this series of seminars that are really interesting. And thanks a lot to everyone also for being here and for attending this. So what I will be presenting today is joint work with Paolo Biuso. So he's a PhD student in ICFO, Barcelona. And actually these results, I mean, they were just published them like around 2 weeks ago. So I'm really excited to share them. But okay, at the same time, I was just finishing the talk yesterday night. So let's see also how this goes. So the motivation is clear. So we all know about the Carnot cycle and how important it is in thermodynamics because it gives a universal bound on the maximal efficiency of an engine given two heat baths at different temperature. But of course, we also know that to reach this efficiency, the power goes to zero, which motivates the whole field of finite time thermodynamics, which I would say it's kind of characterized by the lack of universality. So to find the optimal power and the optimal efficiency at finite time, one needs to really look at the details. Okay, so one needs to look at the working substance. Okay, so which kind of engine we have, which kind of control we have, and so one really needs to understand all the microscopic details. Or macroscopic, it depends on the level of control, but we really need to understand the dynamics of the system to find optimal cycles. And this is why still nowadays, and we are writing books and we are doing research about finite time thermodynamics. And I might say it's also kind of amazing that say after almost 200 years of the famous work by Carnot, we are still investigating, and there are still new things to be said about this finite time thermodynamics. So, say looking at the research in the quantum aspect of it, so for nanoscale engines, and on the last 10 or 15 years, so more or less, roughly speaking, one can see two different approaches. So one is say a phenomenological approach, where the idea is that we take the figures of merit, say the heat, for example, released to the bath, and one makes a reasonable assumption. Okay, so for example, one splits the heat between a reversible contribution and an irreversible one, which here the reversible one is defined by some. So it's proportional to 1 over the time of the process. So when the time goes to infinity, then we are only left with the reversible transformation. And then this depends on some coefficient sigma. And in a way, this coefficient has all the details of the process. Okay, so it's kind of a very compact way of dealing with this complexity. And it's quite nice because just by assuming this simple form, one can already make some interesting statements. So for example, in this famous paper, by expositor, they look at the kind of regions where this efficiency and maximum power is defined. So basically finding the maximum and minimum for this given this form. And one can already learn of the form of these optimal engines. So these results there's been quite a lot of research, and these results have been applied to other engines, and also they have been generalized. So for example, in these two papers, they look at the maximum efficiency for any given power of the engine. And essentially, we see that from these results that they have a wide applicability, that there is a nice way to get trade-offs between efficiency and power. But of course, we don't have a microscopic description. And this also means that we really don't know how to optimize the engine. Okay, so even if we may know what is the region of the optimal engines, once one is given a particular level of control, I mean, if we don't have, if we don't understand the dynamics of the engine, we cannot make also optimal cycles. So then, I wanted to contrast this with a more exact approach. So here the idea is a bit the opposite. So we take a very simple system. So for example, say a two-level system, which is in contact with two baths at different temperatures. So this is a very, let's say, minimal model that we can describe very well, and we can solve almost analytically. So in this case, one can really look, for example, and this is discussed in these different papers for slightly different scenarios and cases, but one can look at really understand the perfect cycle, so the maximal power output perfectly, okay? We also don't need to assume a particular form of the cycle, so we don't need to assume Otto or Carnot cycle, so we really can find the maximal power output. Now, whereas, for example, this is discussed in these two papers, so whereas in principle, there are methods to optimize arbitrary working substances. In general, it really becomes complex, okay? So as we increase the size of the system, and this is normal because also the Hilbert space dimension increases quickly, so one really has to face very difficult optimization problems. So it's very hard to actually make some kind of general or universal statements. Now, in this work that I will present today is kind of a compromise between these two approaches. So we will keep a microscopic description, but still make three important assumptions. So first, we will focus on finite time, Carnot cycles. Second, we will also assume that the relaxation is well described by Markovian dynamics. And finally, and this is very important, we will assume kind of slow driving or linear response. So it basically means that we will stay not so close to equilibrium always, okay? So not quite at equilibrium, by kind of finite first order correction to the equilibrium case. But I mean, these are indeed strong assumptions, but else we will make no assumptions on the kind of working substance we have or the level of control. So we will keep it very general. Now, one of the main reasons that we can make progress in this case is that there's when we are in this regime of being close to thermal equilibrium, there's the geometric description of thermodynamics, which in particular gives us a way to find optimal processes. So these ideas go back to the 70s or 80s in a series of seminal papers. And it's interesting because here, in principle, people initially had in mind really equilibrium thermodynamics and macroscopic systems. And then more recently, for example, Crookes and Sivak and others, they started looking more at nanoscales or stochastic thermodynamics, so try to apply also this framework there. And then it's been also applied to the quantum regime, and more recently with Matteo Scandi and also with Harry Miller and Janet Anders, we've been looking at this geometric approach for, let's say, open quantum systems and also quantum systems with coherence. And a bit also the results that I will be presenting today are based on also these ideas. So let's move on. So let me first briefly describe the Carnot cycle. let's say, the quantum version of this. First, a bit of notation. So I will consider an engine, so say a quantum system that we can derive the Hamiltonian in time, and it's described by some state rho. I will assume that this system either interact with the cold bath or the hot bath, but not simultaneously. And when interacting with the bath, this is described by kind of a standard Lindblad or Markovian master equation, with the thermal state being the unique fixed point. Okay. Now I will also use standard definitions for work and heat. And okay, so let's move on to the cycle. So the cycle has 4 parts. It's well known. So the first one is an isothermal expansion. So basically, we slowly, quasi-statically change the Hamiltonian. And this process is so slow that the state is always in thermal equilibrium. And then, in this case, the work will be given by just a change of free energy between the endpoints. Now, the second step is another expansion, but now this one is the system is disconnected from the thermal bath. So this is adiabatic in the thermodynamic sense because there's no heat exchange with the surroundings, but I wanted to stress that this process can be made arbitrarily fast. Okay, so in particular, we can just make a quench where we can change the Hamiltonian from the last point to this point. Okay, the reason for choosing this is that one can easily see that. So initially, at this point, the system is in thermal equilibrium with the cold bath, and we make this quench in such a way that with respect to the new Hamiltonian, the system is in equilibrium with respect now to the hot bath. Okay, so this quench ensures that there's no dissipation, but indeed it can be made arbitrarily fast. And now finally we go back with isothermal compression and again another quench. So one can see that we again get in this limit when the time goes to infinity, we get 0 power and Carnot efficiency. Now in this work, we're interested in finite time corrections to this limit. So basically this means that in the isothermal processes, we will consider them to be slow, but not quasi-static. Okay, so not infinitesimally slow. So in practice, this means that the state will not be quite at thermal equilibrium, but there will be some correction, and that the work will be given by the change of free energy plus, again, some correction. If one looks now at the power and at the efficiency, so the power now becomes finite with some corrections that depend on the path, on the particular process, and the efficiency will be smaller than Carnot. Good. So now, yes, so you can see that basically the key thing to optimize in this process is the isothermal parts. So let me now introduce this idea of thermodynamic length to describe this. So for this, let's assume that the Hamiltonian that we can modify in time, that's expanded like this. So we have some control parameters and corresponding conjugated observables. Now, so these control parameters, it could be just a, say, harmonic oscillator where we are changing the frequency, or it can be a more complex system like a many-body system where, for example, we can change the magnetization or some global parameter. Okay, so this is just a very general expansion. Now the idea is to expand for small driving. So when this lambda dot is small, so it's kind of linear response. Now in this case, because so we are driving slowly the system. Now, so if we expand around for small velocities, what one finds is that the state is given by the thermal state plus some correction that will only depend on the Hamiltonian and on the first derivative of the Hamiltonian, because that's what we are expanding around. Now, if we plug in this expansion here in the expression for work, we find the reversible term coming from the thermal state, and the dissipation. Now it can be written as follows. So it can be written as kind of a quadratic form. So this comes from this h dot and from the h dot from the first order correction to the state. So this is a linear response expansion. Now, the key idea of say, these papers is to realize that actually we can think of this as a metric, okay? So we can think of this matrix here that is connecting the lambda dots as a metric. And the reason is because you can always make it symmetric. I mean, you find that it's a smooth, except, for example, if you are in a phase transition or in very particular models, this will be smooth in the parameter space. And the fact that it's positive definite, this is very much related to the second law of thermodynamics. So basically, if we have a Markovian system where the dissipation always increases at each point, or the entropy production always increases, then automatically this metric will be, or this matrix will be positive definite. And with these three, we see that this forms a metric. Now, this is nice because then you can think of the dissipation as a kind of length. So in fact, it's more related to the length squared. But what this means is that in this parameter space of the parameters that we can change, geodesics that are given this thermodynamic metric correspond to processes that minimize the dissipation. So this, of course, is a beautiful observation, but in practice, it also means that we can find optimal processes that minimize the dissipation by solving the geodesic equations. This is, of course, still hard, but something worth pointing out is that the size of this variational problem is given by the number of control parameters and not the full Hilbert space. Okay, so that's what makes it also efficient. Because if we have even a many-body system, if we just have one or two control parameters, the number here of differential equations will be small. Okay. So now let me comment a bit on this metric for particular models. So the first one that I want to mention, and I will call it in this talk the standard thermodynamic length, because this was one of the original thermodynamic lengths that was proposed for macroscopic or equilibrium thermodynamics, which is basically the second derivative with respect to the control parameters of the free energy. So it's kind of a susceptibility. And this is kind of a response function in equilibrium thermodynamics. Now, what is nice is that this can be also justified macroscopically. And one finds that this is the right metric when these observables that we can drive in time, they relax to equilibrium exponentially. So here I'm missing x dot. So whenever we have an exponential relaxation of our quantities of interest given some time scale, then we also know that this standard thermodynamic length is the right description, which kind of makes sense because if we have a large complex body, the dynamics are extremely complex, but still we see many times a kind of exponential relaxation to equilibrium. And in this case, we recover this standard result from equilibrium thermodynamics. But one can go beyond. So in particular, if you have some Lindbladian evolution, so this will have many time scales. So if we diagonalize this Lindbladian, there will be many time scales. And in this case, one also can find a metric. And this is what we did with Matteo recently, which kind of extend previous classical results from Crookes, for example. And here, what plays a role is this Drazen inverse, so it's kind of the inverse of the Lindbladian, so I don't want to enter into details, but for example, just to give you an idea, if one assumes a very simple master equation, just an exponential relaxation, so kind of a reset master equation, then we recover the standard thermodynamic. I mean, there are other approaches because this is a very general expansion. For example, one can use Kubo linear response for the full system and path evolution. And this, for example, is nicely described in this paper by Bonanz and Defner. I will not discuss into detail here, but the point I want to make is that this linear expansion is very general, and essentially you can choose your favorite approach, and then you can get a microscopic also description by finding this metric. Okay, so now we can move to the optimization of the cycle. As I was mentioning now, the power will be given by this expression. So we have the reversible contribution minus some dissipation. And now I've also argued that this dissipation can be written as a quadratic form. Now, the first point, and this I don't have time to explain why, but it can be seen that for this standard thermodynamic length, optimal protocols are always symmetric, so they satisfy this property. And for open quantum systems, it's shown in this paper, for example, that they satisfy, they are proportional. Okay, so this entropy production, say, they become proportional one to the other. So let's stick to this one because it's simpler for the moment. I mean, I will then discuss the more general case. And then we can write the power in this quite nice expression. And now we can go back to the results that I was mentioning at the beginning about, let's say, phenomenological thermodynamics, because now we understand this sigma. But let's keep it general for the moment, because now to optimize the cycle, so the first step that we can take is just to optimize over the times. Okay, so basically we take the derivative and we find where this power is maximized. And this is what was done in these famous papers. And it's well known that the efficiency and maximum power for these flow dissipation engines, it's given by the Coulson-Alborn efficiency. And this is the corresponding maximal power. So more recently, in these two papers, this result was generalized in the following sense, because this is the efficiency and maximum power, but one might say, okay, but I don't want to sacrifice all the efficiency for power. So you might care about some trade-off between efficiency and power. So this can be formalized as follows. So say that you want the efficiency to be some proportion of the Carnot efficiency. Okay, so this is from 0 to 1. And then one can find the maximal power for a given efficiency that is defined by this parameter gamma. And this gives this more generalized expression, but essentially they look quite alike. What is crucial for us is that once we have optimized over the time, all is left to do, or let's say all the relevant information is encoded in this ratio. In particular, if we want to maximize the power for any given efficiency, what we want to do is maximize the ratio between delta S squared and the entropy production. So indeed, this is the first crucial observation that independently of the figure of merit that we are taking, so combining power and efficiency, the optimization of the cycle boils down to maximizing, this ratio. But this is non-trivial, okay? And the reason it's very complex is because we want to maximize this ratio over trajectories, so over protocols of the engine, so over, let's say, continuous variations or functionals of the control parameters. Okay, so it's a complex optimization, and then previous works have looked at the case of a single qubit, in particular Paolo, and this kind of motivated us to kind of use this geometric approach to go beyond these simple systems. And it turns out that it can be done, and it's very simple, the proof. So I also wanted to share it. So basically we want to maximize this quantity as a function of all the possible cycles in the thermodynamic space. So let's assume that first let me introduce this a dimensional Hamiltonian. So this is just convenient, okay, because then we don't have to pay attention if we are in contact with the cold or the hot bath. But basically you can think of this G, roughly speaking, as the Hamiltonian that we are varying in time. So as I was saying, we have this quadratic form for the dissipation, and I can think of this as a scalar, as a scalar product between, say, two trajectories. Okay, so in general, this scalar product will depend on the metric, so on my thermodynamic metric, and on the particular path that I'm doing. Okay, so it's kind of just a mathematical way of writing this in a kind of abstract way, but this will be convenient. Now the trick is to realize that also the change of entropy between these points, so if you write it as the integrated derivative of the entropy, one realizes that this you can also write as a similar scalar product, where now this metric is given by the thermodynamic metric the standard thermodynamic metric that I was mentioning before. So now, for simplicity, let's assume that the dissipation is also governed by this standard thermodynamic metric. And now the proof is actually very simple. Okay, so we have this ratio, and basically we have a scalar product squared divided by another similar scalar product. Now, here it's very tempting to just use Cauchy's bars. And then you see that indeed, if one uses Cauchy's bars, the terms that depend on G dot disappear, and we just get that this quantity is upper bounded by the scalar product of G with G. And it's very easy to see that this is nothing but the heat capacity, in particular the heat capacity integrated along the trajectories. And I think this is quite a powerful result, because what it's saying is that you give me a trajectory of so you give me a cycle of your engine, and then if you compute the heat capacity along the cycle, this is giving you an upper bound to the power output of the engine. Now, what this is also telling you is how to optimize the engine, because to saturate this upper bound, what we need to do is to take G dot, so the velocity, to be proportional, so to be parallel, let's say, to the Hamiltonian. So it happens that in a way the simplest protocols, so the ones where given an initial point and just kind of have a time-dependent parameter in front of Hamiltonian, so these protocols saturate this inequality, and they maximize this quantity. Now, this is the first step. And the second step, so you see that the proof is just a single line, is to just realize that the heat capacity, the integrated heat capacity, is maximized by the point where this heat capacity becomes maximum. Okay? And this just tells you that optimal cycles are in fact small cycles around an optimal point where the heat capacity is maximized. So this is kind of the key result of our paper, that we can bound this figure of merit by the heat capacity of the working substance. This holds for the standard thermodynamic length, but it can be also generalized to more general metrics. And I will not enter into details, but let me just say that now the figure of merit, instead of the heat capacity, will be, as expected, a more complex figure of merit that depends on the particular metric that one has, in particular in the inverse. But it's kind of, it satisfies the same, it's in the same spirit, okay? So this is a scalar function that depends on your control parameters, and basically one wants to optimize this scalar function to find the optimal point where to perform small cycles around. And we can also describe how these small cycles look like. So basically the main idea is that indeed it can be generalized and we can give the optimal solution. But of course, still one needs to look for the optimal point. This can be done numerically, or it will depend on each particular case. So let me summarize a bit the results. So basically, for when systems are well defined by a single characteristic time scale, the optimal power of finite time Carnot cycles is given by this relation between power and efficiency times this figure of merit. For generic Limbladians, the same figure of merit appears, but the relation between power and efficiency is more complex, and in particular it will depend on the omicity of the path. So this is a very long expression, but okay, it can be found. Now, what we've done basically is to also optimize this figure of merit around all possible cycles. And what we find is that in this case of a single resolution time scale, this is maximized by the heat capacity of the working substance divided by the equilibration time scale, whereas for this more general case is maximized by a more general figure of merit that depends on the thermodynamic metric. Okay, so some remarks. So the regime of validity is the kind of slow driving or low dissipation or linear response regime. Now, okay, one point that I think is very important to stress is that, so at this point one may say, okay, but what really have you solved, okay? Because we started from a very difficult optimization over cycles, but now we still have to maximize maybe a complicated function over the parameter space. So is it what's the point? No? And the point is that this is a scalar function. Okay, so we start from optimization around all possible cycles or functions, and we go to a maximization over just a scalar function. And this, of course, is much easier. Okay, so it's just you have a figure of merit, and then you choose your favorite numerical method, and just find what is the optimal point in the parameter space. So this is, at the technical level, I would say this is the main achievement of our work. Now, it's also worth pointing out that this optimal point is independent of the figure of merit, which is quite nice. So you have only to do it once. And also the optimal cycles, we can construct them. And for this particular case, they turn out to be very simple, which is quite elegant. So it's one of these cases where in thermodynamics, where the simplest cycles gives the best outcomes. So even if you can optimize over all possible extremely complicated cycles, this one is still the best. And well, okay, I mean, I will not enter this into details, but let me just stress that this is an upper bound, and that sometimes, for example, if you're in a phase transition or in some delicate systems, one has to be careful that to not take it. So this is it will just become an upper bound. Okay, but let's move on. I mean, this is explained in more detail in the paper. Yeah, so I would like now to move to application. So let's first apply it to open quantum systems. So we first consider just the standard, so like in the previous literature, just a single qubit interacting with two baths, give with a standard adiabatic master equation, given a bosonic bath. So indeed, one finds that the optimal cycles are small cycles around a point where the heat capacity is maximized of the qubit, not only in fact the heat capacity, but the heat capacity divided by the time scale of equilibration, which is now governed by the spectral density of the bath. Okay, so one has to optimize this ratio. And then we get the power, the maximal power for any given efficiency. So now I write for high efficiencies because the expressions get simpler. And this result kind of complements previous literature, where what people have looked at is the maximal power, okay, not for a given efficiency, but away of this slow driving regime. Okay, so it's kind of one complements the other. But as I was mentioning before, I think also the strength of our approach is that we can go to more complex systems. So just to illustrate it, now I consider a three-level system where the dynamics are more complex because we will have some coupled master equation, so it will not be a simple exponential relaxation. And here again, we can plot this figure of merit, as I was saying. So this is just plot here. And basically, we can see, for example, that the optimal point is found when these two energies are the same. So when E2 and E1, they are identical, this function is maximized. And then you can look for the particular point. Here, also, what I wanted to compare is this more abstract figure of merit, which is the exact one, to the heat capacity of the working substance. And what we can see is that even if it's not the exact figure of merit, the heat capacity also gives a good idea of what is the optimal point for driving this engine. Okay, so this goes back to what I was saying at the beginning, that even if this standard thermodynamic length is not the exact description, it does give a good approximate description of many systems, okay? And with this, I move to the second part, which is many-body engines. So here, indeed, I will take the heat capacity as the figure of merit. And the idea of it is the following. So, and this is based on some ideas coming from these two papers. So basically, if we have say, n independent, so if our working substance is made of n independent systems, then what one finds is just the power scales linearly with the number of systems, and that the efficiency stays the same if we run the same cycle. But now the idea put forward by first Armen and Karen and others and co-authors was to let's try the following. So if we now let the systems interact, so we not necessarily longer have a linear let's say a linear scaling of the power, but one can use this extra degrees of freedom, says, by keeping the power still scaling linearly, at the same time optimizing the efficiency. So, I don't know if this was very clear, but the idea is to use the interactions to, as we increase the size of the working substance, it becomes more and more efficient. While keeping the power per particle constant, and this is also very nicely described in this paper by Campisi and Fazio. So let me illustrate this a bit for different systems. So first, indeed, one just considers n independent qubits, and this is this green curve here. So we can see that as we increase the size of the system, this figure of merit increases linearly. Now we can start having some interactions, so say an icing chain where we have two-body interactions, and we can see that indeed thanks to the interactions, the figure of merit grows, so we can get better efficiencies as we increase n, even though still eventually we reach also linear scaling because we don't have a phase transition. And now let's get a bit crazy and let's assume that we can do, so here we have two control parameters, but let's assume that we can have full control, so we can change all the parameters of the Hamiltonian. And then this was shown by Rip and Wolf, that the optimal Hamiltonian takes this form, so it's a ground state and many degenerate excited levels. And in this case, it's interesting because the heat capacity grows as n squared. So this clearly allows for something like this. And indeed, so let me discuss this a bit more in detail. What one finds here is that one can make it so that the power stays linearly with the number of components. This is, of course, here they are highly interacting, and the efficiency tends to Carnot efficiency as 1 over n. So it's nice because the same behavior was also obtained in this paper that I was mentioning, but in their case they were optimizing a kind of auto cycle. So they were finding the optimizing the work over all possible unitaries in the adiabatic part of the cycle. But it's quite interesting that we recover the results from a completely different approach, by taking this geometric approach to Carnot cycles. I also wanted to mention that actually this Hamiltonian appears in several papers in the literature. In particular, as I mentioned, so this was initially derived by Rip and Wolf, and they use it to find finite size corrections to Landauer principle. And now also more recently by Luis Correa and co-authors, they use this Hamiltonian to find to design optimal thermometers. And this again is related to the fact that the heat capacity, it measures how good a system is for thermometry. So it's quite interesting that this Hamiltonian keeps popping up in different contexts. And now, I wanted to also briefly mention, of course, it's a very idealized scenario, but if one wants to get this power, so finite power per particle, while efficiency tending to Carnot efficiency, so Campisi and Fazio had a very nice idea to basically use to put the working substance in a critical point. So in their case, they were not really looking at optimization of engines, and they were just considering an auto cycle. But it's quite interesting that with our approach, we also recover the results. So we kind of see that, so this means two things, in a way that it seems that Otto and Carnot cycles become really intimately connected in this limit of optimal cycles. So they provide similar outcomes. And also our results suggest that, in fact, the driving that they were considering in this article, and also essentially the protocol, it might be close to optimal, if not optimal, at least in this regime of slow driving, of staying close to thermal equilibrium. So it's I think, a nice also consequence. Okay, and now coming to the end, I just wanted to briefly mention some projects or open questions that are related to this that I think are interesting. So one is about this small cycle. So as I mentioned, we find that this kind of very small cycles, that they provide optimal power output. And it's interesting to see that in recent works, they also find these cycles to be optimal in the case of, let's say, of qubits, or for exactly solved models, but for any driving. Okay, so for any speed, they find that these are the type of optimal protocols. We have also shown this for arbitrary engines, but again, for slow driving. So, of course, there is a big open question, which is to understand if these optimal cycles of finite-time engines, they always take this form, okay? And I think this would be really kind of a breakthrough, okay? Because it would simplify a lot the kind of, to find upper bounds of finite-time thermodynamics. It would simplify a lot how which kind of process one needs to consider. Another question, of course, are the now famous thermodynamic uncertainty relations. So it was noted in this paper by Holloway and Ryabov that this critical heat engine that I was mentioning, it has diverging work and power fluctuations, and this is indeed because basically the heat capacity is governing the amount of fluctuations. So we see that indeed when we are optimizing power, so at least for these finite time engines, we are optimizing the heat capacity, which also means that we are kind of maximizing the fluctuations. Okay, so it really seems that there's a trade-off, and this was shown here, and in our paper we also see it for the optimal engine. So we also see that as we approach this Carnot efficiency, so the fluctuations diverge, so these TURs are satisfied. But okay, on the other hand, we have also found counterexamples to this. So to me, it's still not clear, and I think it's an interesting question for these driven engines to understand to which extent these TURs apply. And so yeah, I think it's a nice open question. And another one is because there's been a lot of interest in the community about shortcuts to adiabaticity, and they've been used a lot for the Otto cycle. But what about finding similar shortcuts to the Carnot cycle? So I think this is really an interesting endeavor. So, for example, there's been this idea by Dan, Tovalina, and Kozlov to kind of create a shortcut to equilibration. I mean, there's many papers now that with similar outcomes, so this is just one. I also wanted to mention that with Nicola, Matteo, and Mark, we've kind of made an attempt to design this shortcut. So, but I still think there's a lot to do here. And with this, I go back to the talk, let's say, and to the summary. So basically, we developed a general framework to optimize finite-time Carnot engines, which is based on the idea of the thermodynamic length. Optimal cycles turn out to be small cycles around a suitable point, and this is independent of the figure of merit. For the standard thermodynamic length, optimal cycles are the ones that maximize the heat capacity and take a very simple form, which is quite nice. And we apply these results to both open quantum systems and many-body systems, and you can find the results here. And thanks a lot for the attention. Hello?
Are you finished?
Yes, I'm finished.
I'm sorry, I'm watching the live stream, so it's...
Yes. I'm sorry.
No worries. Nice talk, Marty. That was great. Sorry, I just I'm watching the YouTube, so it's slightly delayed from the real time. Okay, so
I was thinking that no one was listening.
yeah, right. No. That's the weird thing about this kind of format. But there's plenty of people talking and a lot of good comments coming in there. Let me just take questions from people now. So there was still a good number of people there, slightly down on numbers, but I guess that's because we have a lot of actual viewers from Brazil and from the US and stuff. But we just thought it was a good idea to vary the time a little bit. So let's take the first question. I see a question coming in there from Patrick Potts, I think. Let me just look back. Yeah, hi Marty, thanks for the great talk. Is there any hope to generalize the concept of thermodynamic length to non-Markovian dynamics?
Yeah, good question. Well, I think it's so it's definitely worth exploring. Of course, it will not be a metric because it can become negative for the reproduction. So then, to me, it's not clear how to deal with this. And I would say essentially I don't know, but it's definitely worth exploring. What can be said with non-Markovian systems?
I see. Let me just ask for more questions. I have some of them, but I'd rather go to the audience. He says thanks. Just wait because it takes some time.
Yeah, no problem.
Janet Anders says, how quantum is all of this?
Well, good question. No, I think probably these insights can also be applied to classical systems. And one of the things that we find that is that actually creating quantum coherence doesn't help you and this was also found before by Seifert and Kai Bradner, that in this linear response regime, creating quantum coherency doesn't help you for the power output. So there's not much quantum in here. But it's also been seen in other frameworks that coherence can help you. So I would say for this particular result, well, it's quantum in the sense that we show that quantum effects don't help you. But that's
yeah.
Let's say.
Sure. Yeah. So I have a question related, or maybe an idea, something that came to me during the talk was that. So I mean, this notion that you have an upper bound on the heat capacity, which is an upper bound on energy fluctuations, is sort of fully consistent with this notion of thermodynamic uncertainty relation that I've been working on and Gabriel Landy's been working on and stuff like that. But furthermore, I mean, there are these old results, I remember in quantum information, where you can kind of witness multipartite entanglement from heat capacity, for example. I don't know, I wonder if something like this can be used to sort of, I don't know, verify. Maybe it's not very useful because in the end, I mean, just to say there's entanglement there doesn't mean it's necessarily functional, I guess, but maybe it's an idea to look into, maybe a way to think about.
Yeah, think about this actually.
Yeah.
I don't know if one can. Yeah, we really didn't look at. Yeah, if by allowing entanglement you can get more heat capacity, but indeed it could be that there's a difference.
I remember that. I mean, maybe somebody in the audience can correct me, but I remember in really like older papers where people tried to kind of witness multipartite entanglement. Maybe Marcus Huber now or someone can tell me with heat capacity. But perhaps I'm wrong anyway. But it's just a point. Yeah. So I have a couple of more comments coming in. Anna Sampera asks, "What happens if we are not in the linear response regime?"
Yeah, great question. I mean, it's a bit what I meant. So maybe I'm wrong, but how I see it is that once you go to away from the linear response regime, it's very difficult to kind of make universal
statements. Yeah.
So, I mean, and it's very interesting, and we can look at particular cases, and then you'll find, for example, that discontinuous protocols are optimal. So though it's quite complex, but I don't know what's the general form of the optimal cycle, and yeah, it's very hard to go beyond.
I guess you can kind of try and fish for corrections there. Maybe that's one of the things you can do. Maybe.
Yeah, or compare, right? How these optimal cycles in the low dissipation regime, they compare to other cycles, and maybe they are close to optimal or far from it.
Yeah. Okay.
Interesting.
Great. And so I have another one coming in here is by someone called Sina. Do you have an idea how a Lindbladian containing counter-rotating terms could have an influence on the results?
Well, so I guess wait. So in this case, I guess it's, or maybe I'm being silly, but then you can get non-Markovian or yeah. So
you haven't really thought about that too much.
Well, I mean, for sure, I mean, we always assume Markovian in that form, and for sure it can be looked at, but I don't.
I see.
The basic, I don't think it will influence a lot, but we haven't investigated.
Thanks. And another question by Janet. Have you compared your slow results to the results by Deschamps, Lutz, and EPL on optimal cycles of a classical harmonic oscillator?
Well, okay, we haven't compared to this specific article, but I would expect that. Okay, I don't know the details, sorry, of this article, but I would expect that if they find the optimal cycle, and if they go to the slow driving regime, one would find that the optimal cycle is the one that maximizes the heat capacity. So I'm pretty sure. Like, I haven't compared, but we compare to other results in the literature, and we always find this.
So remind me again. So there was two terms in this upper bound. You have the heat capacity, but you also have the equilibration time, right?
Yes.
So you can also look for processes with a very rapid equilibration. Would that be right?
Yeah. Sorry. Thanks. This is a very good question. I didn't mention this because actually what happens is that, this is also a very important point, thanks. So what happens is when you maximize the heat capacity, sometimes the equilibration time scale also increases.
Of course, so because that's consistent with criticality, right? You have a critical slowing down. So what you gain in fluctuations, you pay for in a diverging length or diverging time scale.
Yeah. So it's a very important point. So what you want to optimize is the ratio.
Yeah.
And this is really non-trivial.
Absolutely.
So for example, paper of Karen and Armin, they see that for this critical system with many degenerate levels, also the time scale diverges. Okay, so it's really an interplay between these two. Yeah. This is very important.
Yeah. There's another question about non-Markovianity coming in there, just saying, can you explain a bit, how the optimality might be changed if it was non-Markovian, but I guess you don't know.
Sorry. Well, I think there's room for improvement,
Yeah. Any more questions, guys? We'll just wait a little bit. Maybe even if students have something there, I mean, don't be afraid. Marty's here. It's your chance to shine. Just wait a little bit.
Yeah.
There's a delay, so I mean, it takes a little bit of time before they start asking.
Yeah, no worries.
Okay, let me just ask. No, it was a very nice talk, very clear.
Thanks. I was a bit worried because...
No, I mean, this equilibration timescale in particular is interesting for me because I always sort of... I mean, in the end, the old guys, like, even when they were making engines, they knew that steam was good because steam is something that the heat capacity is diverging in, but this timescale issue is a much more subtle thing in the quantum case. But no more questions. Janet has one there. Sorry, Janet, if I didn't see that one previously. Many of the fully solved optimal protocols have delta spikes. You don't allow for spikes, so how much worse is your optimum in comparison to the full optimum?
Yeah, so indeed, this I mentioned that when you allow for exact optimization, you get these discontinuities and these spikes. And so in our case, it's always continuous. I don't know. I think at some point with Matteo, we were comparing the two, and it really depends on the time scale. So if you are in the regime of very short time scales, they can, so the optimal solution can be much better than the low dissipating one. So yeah, that they can. I mean, in their, just I'm saying obvious thing, but in the regime of validity, they both converge. If we are in the regime of extremely short cycles, then the exact solution can become much better than the one we provide.
I see. So there's an interesting question coming in from Marcus Huber. He says, how do you see the costs of controlling the cycle versus the power output? Can they be useful if classically controlled, or do they need to be quantum controlled by clocks, etc.?
Yeah, so I mean, there's definitely control is another very interesting issue. So I'm not familiar enough with this idea of quantum clocks and how. Okay, so I know it, but for me it's hard to tell how it would translate here. What I can say for sure is that, for example, in this Hamiltonian that I was mentioning with many excited states, so in this kind of optimal one, you really need a lot of control. So this very special scaling of reaching Carnot efficiency while having finite power per particle, you can only do this with an increasingly high level of control as you increase the number of particles. So for sure, if you have finite control, at some point you will lose this going to Carnot. Okay? So control, I mean, thanks for the question, because as I didn't mention, control is really important indeed. And if you have limited control, you will not get this upper bound. And also the time scale that you mentioned is really important. So I don't know exactly how
Sure.
The specifics of the question, but it's definitely it plays a role.
So Marty, look, we've been here for a full hour. We might finish it up here. Maybe I'll get divorced in the meantime as well. But thanks very much for the clear talk. If anybody has further questions for Marty about his talk, just fire him an email, and I'm sure he'll easily respond.
Yes, definitely. Yes, thanks a lot, John, and to everyone.
See you, Marty. Bye. Thanks very much for a great talk.
Bye. Thanks. Bye-bye.